Okay, how are you guys? Good? Did you have a good week? I'm good, yeah. So, but it looks like there are fewer of you. I hope we haven't lost anyone. Or maybe it's just the subject is too easy for some people. So, well, we also have this wonderful resource. So, for those watching online, welcome. But do come to visit us sometimes. Yeah. All right, so we are talking about integrals, right? And I know that last week we discussed double integrals and triple integrals. And for double integrals, you talked about integration using polar coordinates. And so this is actually it's a very useful tool for integration. That sometimes things simplify when you use some interesting stuff on the floor. When you use a different coordinate system. We saw that when we talked about as early as like first or second week of the class. Hello, you guys are lacking discipline after not having me for a week. I hope not. So remember that I'm really strict but fair. So all right. So already at the very beginning we saw that many our solutions simplify when we use polar coordinates, for example, in describing curves on the plane. And you saw last week that integration also simplifies. Double integrals simplify if you use polar coordinates. So now the next question is, what about triple integrals? Is there an analog of a polar coordinate system for triple integrals? And how can we use such a coordinate system to effectively evaluate triple integrals? And in fact, because now we are in 3 dimensions, there is more than one choice to make. There are more options. And there are 2 particular coordinate systems which are very convenient in 3 dimensions, which are called cylindrical and spherical coordinate systems. So we will discuss them in turn. First, we'll talk about cylindrical. Cylindrical coordinate system. And cylindrical coordinate system is really just an offshoot of the polar coordinate system in 2 dimensions. In a way, we don't introduce anything new in triple integrals. We use the same tool, which we already use effectively in 2 dimensions. So the way it works is like this. The usual coordinate system, xyz, is replaced by another coordinate system where, on the xy plane, you use polar coordinates. On the xy plane. And we just add the z variable, the way we just added z to x and y. So the result is that instead of the xyz coordinate system, which we normally use, we pass to the coordinate system in which we have r, theta, and z. So x and y get replaced by r and theta in the same way as for polar coordinates, and z is just thrown in as an extra variable. So the formulas expressing these coordinates in terms of these new coordinates are exactly the same as for polars. They are r cosine theta and r sine theta, and then we have the z. And so z we have on both sides, and it's the same variable. Okay? So what is this coordinate system good for? This coordinate system is good for describing objects which are cylindrical. Well, hence the name, right? So what do I mean by cylindrical? A cylinder in general is something which comes from an object on the xy plane by kind of sweeping a surface by using let's say a curve on the xy plane. So a cylinder itself is like that. We take a circle, and if we just move it up and down vertically, we sweep a surface, and that surface is what we normally call a cylinder. Right? So a circle, the equation of the circle on the plane simplifies in polar coordinates. It's r equals r capital, where this is a number, and this is one of the variables, one of the coordinates in the polar coordinate system, and this number is just the radius of the circle. So in other words, it's a circle of radius r. So when we move it upside down, when we move it up and down like this along the z axis, we create a surface in which the equation is the same in 3D. The same equation means that we also have an arbitrary value of z, and therefore we get the cylinder of radius r. And so just like in integrating on the plane in double integrals, it is beneficial to use polar coordinates in describing things related to the circle or to the disk or sectors of the disk or annuli and things like that. It is beneficial to use the cylindrical coordinate system for triple integrals in describing things, in integrating things related to cylinders and various things that you can obtain from the cylinders. Okay? So what does a triple integral look like in cylindrical coordinates? There is an important point which we should not forget, which is that when we pass to a new coordinate system, there's an advantage, which is that some form will simplify, but there is a sort of a price to pay for, which is that we have to insert an additional factor in the integral. Okay? So for polar coordinates, something that was discussed last week. If you have an integral of a function f, dA, you can write it as a double integral in polar coordinates. You have f of r and theta, but then instead of simply putting dr d theta, which you would normally put, you insert an additional factor, which is r. So you get r dr d theta, instead of the usual dx dy, which we would have in a normal coordinate system. What is the reason for this? Just to go over it one more time, because we will now see how it works for cylindrical and then for spherical coordinates. Everything boils down to the area of an elementary object with respect to this coordinate system. An elementary object is a rectangle, which you obtain by saying that x is, say, in this case, 2 coordinates x and y. X between some fixed value, say x0, and x0 plus delta x. And y is between some fixed value, and that value plus some increment delta y. For the xy coordinates, for the rectangular coordinate system, this inequalities describe a rectangle in which one of the sides is delta x, and the other side is delta y. Right? And so the area of this rectangle is simply delta x times delta y. And this is what gives us the expression for dA as dx dy. And so it leads to a description of the double integral as an iterated integral in x and then y, or first in y and then x, by Frobenius theorem. But the key point is the area of the elementary rectangle, which is given by this formula. Now, when we pass to polar coordinates, the analog of this elementary rectangle is the following. We have to look at all points which are given by these inequalities. Say r between r0 and r0 plus delta r, and theta is between some fixed value, theta 0, and theta 0 plus delta theta. And the picture will be different, right? Because this gives us a sector of angle delta theta. And then the condition for r to be between r0 and r0 plus delta r, let's assume that this is r0, right? Just like I'm assuming that this is theta 0. Of course, in this calculation, eventually you would like delta r and delta theta to become very small, whereas r0 and theta 0 are fixed, right? But I'm just drawing this picture. I kind of magnify everything, so it looks like delta theta looks like sort of the same magnitude as theta 0, but in fact it should be much smaller. And so then if this is delta r, this is confined within delta theta, and the elementary object, instead of this one, we get a kind of it sort of looks like a rectangle, but not exactly, because first of all, there's a certain angle here, and these are not straight lines, but these are segments of a circle, right? So what's the area of this? The area of this one, actually we cannot, I mean, we can, but it will be different. It's not so simple to calculate, give the exact answer, but because we're going to take a limit anyway, eventually, we only need a sort of a good approximation to this. And what's a good approximation to this? We can think of this, we can think that when delta r and delta theta are very small, this will look like a rectangle with the size delta r, and what's the other side? Well, this actually has length r0 times delta theta. Right? The segment of a circle of radius r0 confined within the angle delta theta is given by this formula, r0 times delta theta. And so we approximate this by the area of the rectangle with the sides delta r and r0 times delta theta. And the result of this is just the product of this, and we get r0 delta theta delta r. Right? And so that's the r which shows up in the formula for the integral. Here I denoted by r0 because I wanted to emphasize that for calculating this particular area, I fixed r0, I fixed this length. But when we do a general calculation, this will just become r, and delta theta will get replaced by d theta, and delta r by dr in the limit, right? And so that's how we end up with this formula. So this is the only sort of non-trivial thing to remember about polar coordinates. Don't forget to put this factor r, which actually could be a good thing. I made it sound like it's a price to pay that we have been taxed for the convenience of using these coordinates. But actually sometimes, and oftentimes, this could be a good thing. And the typical example is, let's say you have an integral like this, something like 1 minus x squared minus y squared dx dy. So you see, this is complicated, right? This is actually something we discussed. It's kind of similar to something we discussed earlier. This will be very difficult to take just as an integral in x and y. But when you pass the polar coordinates, this will become squared. I'm not writing the limits, but I'm just sort of giving a rough sketch here. This becomes 1 minus r squared, right? And now we get this extra factor r, and then we get the r d theta. And so you see, this actually becomes a much better integral because I can introduce a new variable, let's say t, which is r squared. And if I do that, then dt becomes 2 times r dr. And then this actually gives me 1/2 of dt. And this becomes the square root of 1 minus t instead of 1 minus r squared. And this is much easier to calculate, right? Because the derivative of this is just 1 minus t to the power 3/2 times 2/3, minus 2/3. Whereas for this one, it's much more complicated. Well, imagine if it was like exponential function or something. So then it becomes even worse, right? So sometimes actually having this factor actually works to our advantage. But in any case, we have to remember to insert it to get the right answer. Now, so this was all about the polar coordinates. But cylindrical are not that far away, not that far apart, because for cylindrical, the only thing that changes is that we now throw in an extra variable, namely variable z. So we add variable z, and now instead of double integral, we have a triple integral over some solid, some region in the three-dimensional space. And so we have some f dA, where this dA usually in a Cartesian coordinate system, we simply write as dx, dy, dz, right? But now, if we want to use polar coordinate system, we'll have to write this function as a function of r theta and z, and then we'll have to write dr, d theta, dz. And the question is, what should we put in front? There has to be some factor, and that factor is a factor responsible for the area of the elementary domain, like this. In the usual coordinate system, in the three-dimensional space, when I say usual, I mean Cartesian coordinate system, the elementary object is a box of sides delta x, delta y, and delta z, right? So it's actually no one correct me. What is the mistake here? dv. That's right. See, I'm a little rusty after the break, but do correct me when I make this mistake. So dv, because we emphasize that this is elementary volume. It's volume. It's not area anymore. The a, of course, was for area, and v is for volume. So the elementary volume for this guy is just delta x, delta y, delta z, which gives rise to dx, dy, dz in the integral, and allows us to calculate this integral as a iterated integral, first x, then y, then z, or any other order that you choose. But now we choose this coordinate system, and so we have to be careful. We have to now look at the elementary object in this coordinate system. And what is this elementary object? Well, we just define it in the same way as before by simply. I shouldn't have done it this way. I'm actually jumping ahead. Let's just do it like this. Okay, like this. It really should be cylindrical, so it should be like this. Right? So it is in a way, it's a kind of a it's what you get by combining the two things. In this face, this side of this object looks like this. It's yes. Why is it called cylindrical? Because it's a cylinder, right? Okay. He saved you, by the way, because I was kind of approaching to count how many seconds it will take for you to notice me. But he saved you, so you should thank him. So the cylindrical is called because you make a change on the xy plane, and then you just throw in the z variable. In other words, you change the coordinates just on the xy plane, and then you kind of let the third variable the same as before. So it's the same idea as the idea for, say, taking the circle and kind of just moving it up and down to get this object. No, the circle is fixed, right? It doesn't grow. It doesn't. The radius of the circle is fixed. It's this r capital. right? Just think of a ring which is made of metal or something. You just move it up and down vertically along the parallel to the z-axis, right? So what's the result? You sweep a surface which is the surface of a cylinder, right? You can only use it for, no, you don't use it only for cylinders, but well, what's in the name? You know, it's a name, so it is derived from this, right? But it's not supposed to explain everything we can do with these coordinate systems, right? Any other questions? All right. So what's the elementary volume of this? Well, we already know the approximate area of this. That's r dr, r delta theta, and we know that this is delta z, right? And so the volume is r delta r delta theta delta z. So it's the same r which we had, or maybe if you want r0, if you want this to be r0, the same r which we had in the calculation of the polar coordinates. So the bottom line is this factor is exactly the same as in the polar coordinate system. It's not more complicated. Okay? So that's the formula we're going to use. And now let's do an example. Let's do an example. So evaluate triple integral over e of the function e to the z, where e is enclosed by the paraboloid z equals 1 plus x squared plus y squared. The cylinder x squared plus y squared equals 5, and the xy plane. Okay. So actually, let me draw a bigger picture. So the paraboloid looks. What does the paraboloid look like? It starts at the point 1 on the z-axis, and it opens up like this, right? And the cylinder is, okay, I just erased it. So that's the cylinder. Let's assume that this is radius. This is going to be radius square root of 5, right? Because we have 5 is the square of the radius, as always. So the radius itself is square root of 5. And so that's the circle at the base of the cylinder. And we want the figure which is a solid, which is confined by this, by the paraboloid, by the cylinder, and by the xy plane. So it is the inside of this. So it's kind of concave. The surface is kind of concave. It goes inside, right? It's like a fancy glass. So what we need to do is to calculate the integral over this. This is our region E of the function e to the z. So when you do triple integrals, then you have to write it as an iterated integral. Okay? So you have to choose in which order you're going to integrate. So you're going to end up with an integral. So you have e to the z. Here actually z is one of the variables, so we just write it like this. This is good, right? Because z is one of the variables in the cylindrical system. And then you're going to have r. Let me emphasize this r again. That's the same r as before. And then we have r dr, d theta, and dz. So now we want to write it as an iterated integral. So you have to choose in which order to integrate. Okay? So what's the best way to do it? For the cylindrical coordinate system, it's always, you see, the point is that you have to choose what the base of this. Actually, this is the general approach to when you have to choose the order. You have to see what's a good projection of your object. Is there a good projection onto, say, xy plane or yz plane or zx plane? That's the first question. And once you have a good projection, everything projects onto something nicely, right? So in this particular case, it certainly does project nicely onto the xy plane. It projects just onto the disk, onto z, which is r less than or equal to square root of 5. The disk over radius square root of 5, right? So that's this yellow. Let's draw it as yellow. And then for each point in this disk, we'll have to integrate. So first of all, we'll have to integrate over the disk. And this will be I'm talking about the outer integration. I'm starting from outside. Right? When you project onto this, you are choosing the first two variables, which normally, if we were using x and y and z coordinates, that would be integrating first x and y. Then you decide between x and y later. But first we choose the first two, and then you choose which one goes first. Right? So that's the strategy which I propose. That you're going to end up with 3 different integrations. Right? So the last one will be the integration over the remaining variable with respect to this projection. So here I project onto the xy plane. So this will be dz. But let's now see what happens here. So this is going to be in the usual coordinate system, in the Cartesian coordinate system. This would have been just dx dy, which you would have to decide dx dy or dy dx. And once you decide, then in the last integration, you have the freedom to choose what x and y are. So that means that you have a point here, x, y, inside, and then the limits will be the limits. You have to sort of draw the segment starting from the bottom of this object to the top of this object, which in the case from this disk, which is part of the xy plane, to this paraboloid. And you would have to integrate in the last integration. You would have